Put 23 people in a room, and there's a better than even chance that 2 of them share a birthday. Seriously, keep your eye on these little dots. Each one lands on its birthday, and there, February 9th gets hit twice. 23 people, 365 possible days, and somehow a collision is already more likely than a clean room. That feels wrong. If I asked you to guess the magic crowd size, you'd probably say something around 180. I did. My first guess was embarrassingly close to half of 365, because apparently my brain saw a fraction and clocked out. The actual probability with 23 people is about 50.7%. So if we could replay this room over and over with fresh birthdays, matching rooms would narrowly beat non-matching rooms. I'm withholding the reason for a second because there's a very convincing wrong way to think about it. You pick one person, compare their birthday with everyone else, notice there are only 22 chances to hit one specific day, and conclude that a match should be rare. That calculation is perfectly respectable. It just answers a different question. The room isn't waiting for somebody to match you. Every person can match every other person, and those possible pairings pile up much faster than the head count. The weirdness lives in the gap between 23 people and the number of relationships hiding among them. So let's empty the room, bring everyone back one at a time, and watch exactly where our intuition loses track. With one person, a shared birthday is impossible. The second person has one date to avoid, so their chance of keeping the room clean is 364 out of 365. Pretty safe. Person 3 has 2 occupied dates to avoid, making their clean chance 363 out of 365. Person 4 gets 362 safe dates. You can already see the trap closing, though it closes quietly. Nobody arrives with a 50-50 chance of causing trouble. Each new person is only a little riskier than the last. The room becomes unlikely through accumulation. Think of a clean run as a very fussy machine. For everybody to have different birthdays, person 2 must miss the first birthday, and person 3 must miss both earlier birthdays, and person 4 must miss all 3. Every single miss has to happen. One collision anywhere ruins the streak. So the probability of a clean room is 364 over 365 times 363 over 365 times 362 over 365, continuing until the 23rd person gets only 343 safe days out of 365. Those fractions all look close to 1. That's what makes this sneaky. Multiply enough almost ones together and they stop being almost 1. At 23 people, the product is about 0.493. In other words, the clean room survives only 49.3% of the time. The yellow collision gets everything left, about 50.7%. This backward route is the key move. Calculate the chance that absolutely nothing matches, then take its opposite. But why is that backward calculation so much easier than counting matches directly? Counting the clean rooms was easy because every clean arrangement has one simple rule. All birthdays are different. Counting matching rooms gets messy immediately. Maybe exactly 1 pair matches. Maybe 2 separate pairs match. Maybe 3 people share one birthday. Maybe a triple appears alongside a pair, like the world's least exciting conspiracy. All of those cases belong in at least one match, and several can happen together. If we add the chance of Alice matching Ben, then Alice matching Cam, then Ben matching Cam, we've counted the all 3 same outcome multiple times. Fixing that means subtracting overlaps, then adding back deeper overlaps, and soon the calculation looks like it has developed a personal grudge. The opposite event avoids the whole mess. Either every birthday is different or at least one birthday repeats. Those 2 possibilities cover everything and never overlap. That is why the single subtraction works. This trick shows up everywhere in probability. If a question says at least 1, there's a decent chance its opposite says none, and none is often much cleaner. Honestly, I missed this pattern for years because subtraction felt like a shortcut I hadn't earned. It is fully legal. Probability doesn't give bonus points for suffering. Now we have the exact calculation, but it still hasn't explained why 23 is so small. A chain of fractions gives the answer without giving our brains much to hold. The picture we're missing is the number of possible pairs, because 23 people secretly create far more than 23 opportunities for a coincidence. Here's what 23 people are actually carrying into the room: 253 distinct pairs. Person 1 can pair with 22 others. Person 2 has 21 new partners left. since their connection to person 1 was already counted, then 20, then 19, all the way down to 1. Add those and you get 253. Another way is 23 times 22 divided by 2. The division by 2 fixes the fact that Alice with Ben and Ben with Alice describe the same pair. This is the part that rescued the paradox for me. We aren't making 23 lonely guesses at a calendar. We're giving 253 pairs a chance to agree. Each particular pair has only a 1 in 365 chance of sharing a birthday, which is tiny. Yet 253 tiny chances is enough to make a collision feel plausible. Careful though, we can't simply say 253 divided by 365 equals the probability. That gives about 69%, which is too high. The pair events overlap and depend on one another. If 3 people share a date, 3 matching pairs appear at once. Still, 253 over 365 is useful as a rough measure of how much collision pressure has built up. With 10 people, there are 45 pairs. With 23, there are 253. With 50, there are 125. Pair counts grow roughly like the square of the crowd size. Double the people, and you get about 4 times the opportunities. That square growth is the real engine, but it leaves a deliciously specific question. If there are 365 birthdays, why does the halfway point land near the square root of 365 rather than exactly at it? The square root gets us into the neighborhood because collisions become common when the number of pairs becomes comparable to the number of available birthdays. If there are n people, there are about n squared over 2 pairs. Set that rough pair count near 365, and n lands around the square root of 730, about 27. That's already shockingly close to 23. For the actual 50% threshold, we need a slightly subtler target. The probability of no match is a product of terms like 1 minus 1 over 365, 1 minus 2 over 365, and so on. There is a lovely approximation for products like this. 1 minus a small number behaves roughly like e raised to the negative of that number. Apply that repeatedly, and the clean room probability becomes approximately e raised to negative n times n minus 1 over twice 365. I know, E just walked into a birthday party, uninvited. It does that. We want this probability to equal 1/2. Taking logs gives n times n minus 1 over twice 365, approximately equal to the natural log of 2. Solve that and you get about 22/99. So the first whole crowd at or above 50% is 23. The constant log 2 nudges us below that rough 27-person estimate. More generally, with d equally likely possible birthdays, the halfway crowd is about the square root of 2d log 2, or about 1.177 times the square root of d. That is the portable version of the paradox. Give me the number of boxes, and I can estimate how many random objects it takes before 2 land together, which means this birthday party is secretly teaching a rule about collisions almost everywhere. Replace birthdays with boxes and people with balls, and the same mathematics keeps working. Toss random balls into D boxes. A collision happens when a ball lands in an occupied box. With 1,000,000 boxes, you might expect to need something close to 1,000,000 balls before duplicates become likely. The square root rule says the halfway point is only about 1,177 balls. That gap is enormous. Computer scientists meet this constantly. A hash function takes large pieces of data and assigns each one a shorter digital fingerprint. If the fingerprint has 1,000,000 possible values, collisions become likely after roughly 1,000 random inputs, assuming the outputs are spread evenly. For a 128-bit fingerprint, the number of possible values is absurdly large, around 3.4 times 10 to the 38. Yet collision resistance behaves more like 64 bits because the dangerous input count grows with the square root of the output space. This is called a birthday attack. Nobody brings cake, which feels like false advertising. The same logic applies to randomly generated IDs, file checksums, license codes, and any system that treats unlikely for one pair as unlikely across the whole crowd. Scale creates pairs faster than most systems expect. Here is the catch though. Our clean formula assumes every box is equally likely and each toss is independent. Real birthdays fail that assumption. Some dates are more popular, seasons matter, scheduled births matter, and February 29 is sitting in the corner being difficult. So does messy human reality weaken the paradox or make collisions arrive even sooner? Uneven birthdays usually make matching more likely. Imagine an extreme calendar where half the population is born on one day. You'd barely get through introductions before that date became crowded. Uniform randomness is actually the arrangement that spreads people out most effectively. Once certain dates carry extra probability, people bunch together, and bunching creates collisions. For two people, the chance of a match is the sum of each date's probability squared. If every date has probability 1 over 365, that sum is 365 copies of 1 over 365 squared, giving 1 over 365. If some dates become heavier and others lighter, squaring exaggerates those heavy dates so the total match chance rises. That's a compact argument, though real group calculations still need the full distribution. Independents can fail too. Twins share a birthday for a very obvious reason. A room drawn from one school year, workplace, family, or maternity ward may have its own patterns. Usually, birthday paradox demonstrations quietly exclude twins and treat people as independent samples. Leap day barely changes the headline result. Using 366 equally likely dates still gives 23 people a probability just over 50%. Using actual birth frequencies also leaves the threshold around the same neighborhood and often raises the match probability slightly. So 23 isn't a sacred number carved into probability itself. It belongs to a particular model and a particular threshold. Independent people, roughly 365 possible dates, and a target of 50%. Change the target, and the crowd changes. At 90%, how many people do you think we need? The answer is still nowhere near 365. For a 90% chance of at least one shared birthday, you need 41 people. At 50 people, the chance is about 97%. At 57, it passes 99%. So a medium classroom is already deep into collision territory. Watch the probability curve. It starts almost flat, bends upward, crosses half at 23, then keeps climbing toward 1. There is no sudden physical switch at 23. 22 people already give about 47.6%. 23 merely becomes the first integer crowd, where a match is more likely than no match. This distinction matters because the phrase only 23 people are needed can sound like a guarantee. It isn't. You can put 23 people in a room and get no shared birthday. That happens about 49.3% of the time, nearly half. A guarantee requires 366 people under the usual 365-day model. Then the pigeonhole principle takes over. More people than dates means at least one date must contain two people. Probability has left the building. Between 23 and 366, we're moving from likely to nearly certain to logically unavoidable, and those are three different claims. I once mixed up 99% with guaranteed while explaining this, which is a fun way to discover how quickly 1% finds an audience. Even with 365 people, there is a fantastically tiny chance that every single person has a different birthday. Each day would be represented exactly once. So the paradox isn't really that a collision can happen early. The sharper surprise is how quickly possible becomes likely, while certainty remains hundreds of people away. Now for the calculation that causes most of the confusion. Suppose you're in the room and you ask, "Does anyone share my birthday?" With 23 people total, the other 22 each have a 1 in 365 chance to match you. The probability that at least one does is about 5.9%. That is small, and your intuition was right about it. The famous 50.7% answers a broader question. Does any pair in the entire room match? You are one dot with 22 connections. The room contains 253 connections. Those questions sound similar in casual speech, which is why the result feels like a trick. There is no trick. The target quietly changed. If we wanted a better than even chance that somebody matches your specific birthday, we'd need 254 people in the room, including you. Then there are 253 other chances to hit your date, and the probability finally passes 50%. So remember the pink dot. If the question highlights one chosen person, count connections touching that dot. If the question allows any pair, count the whole web. This same distinction appears in coincidences outside birthdays. What are the odds I meet someone with my exact password? Is very different from what are the odds any two users chose the same password. The second system may have collisions everywhere, while your own value remains unique. The room-wide question grows quadratically because everyone compares with everyone. The personal question grows only linearly because every new person adds one connection to you. That, more than any formula, Is the intuition worth keeping? There is another number hiding here, the expected count of matching pairs. With 23 people, there are 253 pairs, and each pair matches with probability 1 over 365. Add those probabilities, and the expected number of matching pairs is 253 over 365, about 0.693. That earlier wrong calculation has returned with a new job. It does not give the probability of at least one match. It gives the average number of matching pairs across many rooms. Those numbers differ because one room can contain several matching pairs. Suppose 3 people all share June 12th. That single birthday cluster contributes 3 matching pairs: Alice Ben, Alice Cam, and Ben Cam. A room with 4 people sharing a date contributes 6 pairs, so some collision rooms pull the average upward with multiple hits. This is a useful probability habit. Expected count and probability of any occurrence are related, yet they answer different questions. Expectation can even exceed 1 while a no-match outcome remains possible. With 28 people, the expected matching pair count passes 1, but the probability of at least one match is about 65%. The beautiful part is that expectation needs almost no independence. We assign each pair a little indicator, 1 if it matches and 0 if it doesn't, then add them. The expected total is the sum of their individual expectations. Probability lets us add averages even when the events overlap. That trick is called linearity of expectation, and it is frankly one of the best bargains in mathematics. Now we can measure both the chance that chaos begins and the amount of chaos we expect after it does. If the multiplication still feels suspicious, we can make the room run the experiment. Number the days from 1 to 365. Generate 23 random numbers, 1 for each person, and check whether any number repeats. Reset and do it again. After 10 runs, the percentage may wobble wildly. After 100, it usually starts settling. After 10,000, it hugs 50.7%. A simulation doesn't prove the formula, but it gives the idea somewhere physical to land. You can also watch the first collision time. Most runs stay clean through the early teens. Then failures begin arriving quickly. Some rooms collide almost immediately. A few survive surprisingly long. The first repeated birthday averages around the mid-20s, though average stopping time is another question from when does the probability pass 50%? Probability loves collecting near identical questions and giving each one a different answer. My least favorite hobby is discovering that after doing the algebra. There is a neat way to visualize every trial as a row. Blue squares mean each arriving birthday was new. The first yellow square marks a repeat, and everything after it can be muted because the event has already happened. Stack thousands of rows, sort them by where yellow first appears and a curved boundary emerges. Draw a vertical line at person 23, and just over half the rows have turned yellow by then. That picture contains the product, the threshold, and the randomness all at once. It is the frame I'd keep if every equation had to disappear. The same curve can tell us how large an identifier space should be. Suppose an app generates 1 million random user codes, and we want the chance of any duplicate below 1 in a billion. The birthday approximation says the collision probability is roughly 1 minus e, raised to negative in times and minus 1, over twice the number of possible codes. When the target probability is tiny, that is approximately n squared over twice the code space. Rearranging says the code space should be around n squared divided by twice the tolerated probability. Plug in 1 million users and 1 in a billion risk, and we need about 5 times 10 to the 20 possible codes. That corresponds to roughly 69 random bits. Add a safety margin, account for imperfect generation, and engineers may choose 96 or 128 bits. This is where the paradox stops being a party fact and starts finding bugs. A developer sees 1 trillion possible IDs and thinks 1 million users barely make a dent. Yet the system checks all user pairs implicitly. 1 million users create roughly 500 billion pairs. There's that square again, quietly ruining everyone's afternoon. Of course, many systems can detect a collision and retry, which changes the practical risk. Some need adversarial security, which changes it further. The probability model has to match the consequence. Still, one lesson survives every version. Compare the number of possible pairs with the size of the space. Counting objects alone hides the pressure. Now there is one last oddity. We have treated same birthday as exact equality, but what if close birthdays count too? If two birthdays within a week count as a match, the room becomes crowded much faster. Each person's birthday now threatens a neighborhood of dates rather than one exact point. On a circular calendar, a date can conflict with the 7 days before it itself and the 7 days after it, depending on the rule we choose. That is up to 15 dangerous dates per person. The neighborhoods overlap, edge cases wrap around New Year's, and the clean product needs more care because occupied forbidden regions can merge. Still, the pair count intuition works immediately. Each pair now has roughly 15 chances out of 365 to qualify instead of 1, so the threshold crowd shrinks by about the square root of 15. 23 divided by that is around 6. A tiny group can have 2 birthdays within a week with surprisingly high probability. The exact answer depends on whether within a week means 7 days apart, a 7-day window, inclusive endpoints, and whether February is feeling cooperative. Honestly, the notation is easier than agreeing on the English sentence. This version reveals what the original paradox is really sensitive to. Collision thresholds depend on the size of the outcome space and the width of what counts as a collision. Make the space smaller, allow fuzzier matches, or create popular regions, and coincidences arrive earlier. Make the space larger and spread probability evenly, and they arrive later, though still around a square root scale. We began with 23 dots and 1 yellow birthday. The deeper object was the invisible web, connecting every pair. And here's the thing that still bugs me. In a big enough room, even the coincidences you decided were meaningless become practically unavoidable.